Welcome back. We have finished writing this summary of how we analyze and sketch graphs of rational functions, and let's look at these two examples. Note first of all that in both examples the numerator and the denominator are already factorized, and so the first step doesn't really apply. But typically the first step, factorization of the numerator and denominator, is usually the most difficult one. So let me add a page. And start solving example A. We need to sketch this graph using the summary that we wrote. In part A, the graph is x plus 2 times x minus 3, x plus 1 squared, x minus 2. All right, since both the numerator and denominator are already factorized, we start immediately with finding vertical asymptotes and points of removable discontinuity. The roots of the denominator are -1 and 2, and neither of them is a root of the numerator, so both -1 and 2 are vertical asymptotes. Next, let's determine the behavior of f near vertical asymptotes. All right, at -1, the limit from the left we know is infinity. The question is, what sign will that infinity have? When x is to the left of -1, x plus 2 is roughly 1, x minus 3 is roughly -4, x minus 2 is roughly -3, and this is always positive. So the whole fraction is positive. Now it's easy to see that the behavior from the right of -1 is the same. That is because x plus 1 is raised to an even power. Now at 2, on the left, we have this is roughly 4, this is roughly -1, this is positive, and this is negative. So at 2 from the left, we have positive infinity. Now at 2 from the right, we have negative infinity. That is positive, that is negative, that is positive, that is positive. The fraction is negative. Now, how about horizontal asymptotes? For horizontal asymptotes, specifically for the horizontal asymptote, we compute the limit of f at infinity. And to do that, we know that the degree of the numerator is 2. It's a quadratic polynomial. And the degree of the denominator is 3. It's a cubic polynomial. When you expand the square, it'll be x squared. And when you multiply this by this x, it'll be x cubed in the denominator. So the limit at infinity is 0, since the degree of the denominator three is greater than that of the numerator, which is 2. So we know that y equals 0 is a horizontal asymptote. Now zeros and behavior at zeros. Zeros are the zeros of the numerator, provided that they're not zeros of the denominator. In our situation, the numerator and the denominator don't share any zeros. So zeros of f are those of the numerator, negative 2 and 3. And they're both crossings. That is because the corresponding factors are raised to an odd power, power 1. Now let us find the y-intercept. F at 0 will be 2 times negative 3 over 0 plus 1 squared is 1, negative 2. The value is 3. And now we can draw the sketch of our function. Vertical asymptotes are negative 1 and 2. the value at 0 is 3. Now, the behavior to the right of -1 and to the left of 2 is both positive infinity. So we can draw this piece. Now, to the right of 2, we have negative infinity. We have at 3 this was supposed to be -2, of course. We have at 3 a crossing, and we have 0 a horizontal asymptote. So this information tells us that the graph will look like this. To the right of 2, negative infinity, crossing at 3, and asymptote at y equals 0. Now to the left of -1, we have positive infinity, we have a crossing at -2, and we have asymptote at 0. Note that our knowledge of the behavior near vertical asymptotes was particularly helpful. That is the graph from part A, and in part B, we have a similar analysis. In B, our function is one half times x plus 2 squared x minus 2 over x minus 1 squared x minus 3. All right, so we start with vertical asymptotes, endpoints of removable discontinuity. Vertical asymptotes are 1 and 3 because these are the zeros of the denominator, but not zeros of the numerator. Now, we determine the behavior near vertical asymptotes. Limit at 1, either from the right or from the left, is the same. That is positive, that is positive, that is negative, that is negative. So limit is positive infinity. And limit at 3 is from the left. This is positive, this is positive, this is negative. Excuse me, this is positive, and this is negative. So the ratio is negative. And limit at 3 from the right is positive over positive, so the fraction is positive. Now, is there a horizontal asymptote? For that, we compute the limit at infinity of our function f. And to compute this limit, we note that both the numerator and the denominator are of degree 3. If you were to expand the parentheses, you would find that the leading term in the numerator is x cubed, and the leading term in the denominator is 2x cubed. And so the limit at infinity is simply the ratio of the leading coefficients, which is 1/2. That means that y equals 1/2 is a horizontal asymptote. Now what about zeros? And how our function behaves near zeros? Since the numerator and the denominator don't share any roots, the roots of f are those of the numerator, namely -2 and 2. -2 will be a touching because x plus 2 is raised to an even power. And 2 will be a crossing because x minus 2 is raised to an odd power. Now, the y-intercept is one half times two squared times 0 minus 2 over 0 minus 1 squared, 0 minus 3. That's 1 half times 4 times negative 2 over negative 3. And that is 4/3. So this information, I believe, should be enough to draw the graph, or at least a sketch. Vertical asymptotes at 1 and 3. How does our function behave in between the asymptotes? Well, first of all, note that there will be a root at 2. Also note that to the right of 1, our function is positively infinite, and to the left of 3, it's negatively infinite. So we should expect a behavior like this. Now, to the right of 3 and to the left of 1, our function will behave differently. Let's draw the horizontal asymptote 1/2. To the right of 3, we have f positively infinite, and then approaching our horizontal asymptote. Note, by the way, that our analysis doesn't answer the question whether it will go like this or it will cross the asymptote and go like this. This is why we're calling it a sketch, not a graph. And to the left of 1, what's interesting to the left of 1? Well, we have a touching at -2. That's very interesting. We have y-intercept at 4/3. That's above. And we have horizontal asymptote y equals 1/2. So the graph will look like, or the sketch will look like this. we touch at -2. Then to the left of 1, our function is positively infinite. All right, that is the graph of the function 1/2 times x plus 2 squared, x minus 2 over x minus 1 squared times x minus 3. And again, note that we couldn't, for instance, know that here the graph will go like this. Why not like this? After all, to the left of -2, or rather, to the left of 1, our sketch intersects with the horizontal asymptote. Why can't it intersect with the horizontal asymptote here? Our analysis doesn't answer this question, and so if your sketch is like this, it should also be deemed correct. Finally, I would like to show you another example where you have to do the opposite thing, write down a possible expression for the rational function whose graph is shown. So we again start with identifying the asymptotes. Looks like the asymptotes are at 2 and -1. There are no points of removable discontinuity, so -1 and 2 will be the roots of the denominator, but not the roots of the numerator. Perhaps in some power times x minus 2, also perhaps in some power. Now, where do we have, what can we say about these powers? Well, at 2, we see the behavior at 2 is the same, which tells us that x minus 2 is raised to an even power. And at -1, the behavior changes. It's infinitely positive here and infinitely negative here, which tells us that the power for -1 must be odd. Now, what about the roots? The roots are -2 and 3. So we should have in the numerator x plus 2, perhaps in some power, and x minus 3, perhaps in some power. Both roots are crossings, so the powers must be odd in both cases. We should add a constant to allow for some freedom for our function to move at 0. And it also looks like the x-axis is a horizontal asymptote. Which means that the degree of the denominator exceeds the degree of the numerator. So let's try to take f in the form where these powers are both 1. This power is also 1. And the other power is 2. So I took the smallest possible choices and note that the degree of the denominator is greater than the degree of the numerator. That will make the x-axis a horizontal asymptote. Now, how do we find the constant? Of course, we find the constant using the fact that f at 0 is negative 2. If we plug 0, it'll be constant times 0 plus 2, 0 minus 3, 0 plus 1, 0 minus 2 squared. That constant times negative 6 over 4, and that is negative 2, as we see in the picture. So from here, the constant is 2 times 4 over 6, which is 4/3. So it looks like we can try our function. We can try to write the answer in the form 4/3 times x plus 2 over x minus 3 over x plus 1 times x minus 2 squared. Let's check our answer against common sense. Let's, for instance, see that limit of f at 2 from either side is negative infinity. Well, when x is close to 2, this is positive, this is negative, this is positive, this is positive. So the ratio will be negative. Let's check that the limit at negative 1 from the right is negative infinity. When x is close to negative 1, this is positive, this is negative. Because x is greater than negative 1, this is positive, and this is also positive. So the ratio goes to negative infinity. Let me show you that this is one answer that is sensible, but it's by far not unique. There are other sensible answers. I didn't know for sure that these powers are 1, 1, 1, and 2. I could as well take other powers. There could be other sensible answers. We could look for f in the form constant times x plus 2, x minus 3, x plus 1, x minus 2. Let's say we take different powers, odd, 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 even. Let's say we take powers 1, 3, 5, and 6. The numerator will be a polynomial of degree 4, and the denominator will be a polynomial of degree 11. And so again, the x-axis will be a horizontal asymptote. So this time, to find the constant, we again compute f at 0. So it's constant times 2 times negative 3 cubed over 2 to the power 6. So that's constant times negative 27 over 2 to the power 5, that's 32. And that is negative 2. So the constant is 64 over 27. And so we could write the answer in the form 64 over 27 times x plus 2, x minus 3 to the third power, x plus 1 to the fifth power, x minus 2 to the sixth power. Let's again see that our function indeed is negatively infinite at 2 from either side. This will be positive, this will be negative, and in an odd power, this will be negative. This will be positive because this is roughly 3, and in an odd power, that's still positive. And this is always positive. So the ratio is negative. Let's check that to the left of negative 1, we are infinitely positive. To the left of negative 1, this is roughly 1, so it's positive. This is roughly negative 4 to the third power is negative. To the left of negative 1, this is negative, and in the third power, it's still negative, and this is always positive. So the entire fraction is infinitely positive as x goes to negative 1 from the left. So even though there are infinitely many sensible answers, not every answer, of course, is sensible. So be careful here. You will have a chance to practice this more in your homework. All right, this example finishes this topic and finishes Module 4. Thank you.